Thank you so much for that introduction, Ben. Let me set up my stuff here. Okay. Yeah, let's see. I have slides, right? Great, awesome. Yeah, thank you so much. Yeah, as Ben mentioned, I have been working on this thing called polynomial functors since the start of the pandemic, actually. And I want to try and talk to you about them today. I study polynomial functors, and what I study belong to an area of math that's a little bit niche. It's called applied category theory, which to a lot of mathematicians can seem like a bit of an oxymoron because category theory is known for being notoriously abstract. But today I want to show you, hopefully, that it doesn't necessarily have to be that way by giving some concrete examples. And if you've never heard of category theory before, or if you've heard of it, a more common experience, you've heard of it and you've been scared away, hopefully this will still be somewhat interesting to you, and I can give you the reason of why I find applied category theory so fascinating and why you could apply something that seems so abstract. Next slide, please. Thank you. I can talk a little bit while we wait. Oh, awesome. Yes. So yeah, I'll go over sort of why, I'll try to justify why I'm interested in category theory. Then I will explain this particular category that we're studying involving modeling interaction. And then I'm going to talk about what that has to do with polynomial functors, why we call those polynomial functors. Next slide, please. That was the last slide. Thank you. Yeah, why category theory? Next slide. Sorry, there's a lot of these. Awesome. Okay, so here we have, I'm going to show you a bunch of sort of like entities, sort of structures from math or computer science or what have you. And I'm going to see if we can spot a pattern here. So first of all, this is an example of some signatures for some functions in Haskell or some other similarly syntaxed type functional programming language. And you might know, if you've ever worked with Haskell or something equivalent, that a function f from the pair of types A and B to a third type C can be considered equivalent to a function where the input to the function is just that first type A, and it takes you to a function from B to C. And there's this equivalence here that works really nicely. It almost just pops out of nowhere and it just works. And this is called currying. And yeah, that's just a pattern that you might see. Next slide. We also, yes, here's another example. In logic, we talk about, we have statements, if something, then something, right? It's this kind of, we have truth values, these entities expressed by these variables X, Y, and Z, and we have these statements. I can think of these as inferences that tell you how one truth value might affect another truth value, and you have these entities and these transformations. And great, let's see. Okay, yeah, and so in this logic, we also have this equivalence between these inferences where if you say something like if X and Y are true, then Z is true. That's actually equivalent to the statement if X is true, then Y implies Z. So there's that kind of equivalence there. Again, next slide, please. Yeah, here's an example from slightly more mathy, right? We have this notion of vector spaces where we can take the tensor product of two vector spaces if one's, which is formed by pairwise elements of the basis elements of each of the individual vector spaces. And if we have a function, if we have a linear transformation from a tensor product into another vector space, that's actually equivalent to a linear transformation from one of the original vector spaces to the vector space formed by actually all of the linear transformations between these two vector spaces V and W. And so again, we have these entities, these vector spaces, and these sort of transformations, namely linear transformations between them, and they satisfy this kind of very similar pattern. And so when we step back and look at what is happening here, which is the kind of thing category theorists do, you might see that there's something recurring here, right? We have these entities, and we have these transformations between them. You could think of them, sometimes they're functions, sometimes they're sort of like, they're like directions of data flow. There's some sort of relationship. And so we can express these in a setting called a category. Next slide, please. And if we sort of abstract away what's happening, really we just have these sort of entities, what I'm going to call objects, P, Q, and R, and we have these sort of relationships between them, and I'm going to call these arrows because I'm drawing arrows for them. Next slide, please. I think I'm just calling these. Yeah, and these are within a setting called a category. Next slide, please. Yeah, so that's what we mean roughly by a category, right? And we can, but there's something else in common with these, right? Not just these objects and these arrows. We also have this binary operation that's happening here. First, we have pairing types together. Then we have this AND operation. Then we have this tensor product. And so, all of these take two objects and give you a third object that kind of represents combining these two objects in a really natural way. Next slide, please. And we call this a kind of category that has this structure, a symmetric monoidal category. Symmetric because actually if you switch X and Y, A and B, the first two things in all of these, it's actually in some sense equivalent. Monoidal, you should think about monoids, if you know what that is. Basically, the idea is there's a binary operation that works nicely. Next slide, please. But we also have this third sort of part of the structure, which is that whenever we have a arrow out of something formed by this binary operation, we have this equivalence that we can express by taking part of the thing that we're combining together, taking this Q and putting it on the other side of the transformation. And in some sense, we can express the fact that when two sort of entities, two objects are combined together and there is a transformation out of them, you can actually just focus on one of those two objects and then sort of express the transformation out of it as some sort of relationship, some other object expressing the relationship between the other two objects. And this kind of structure is called a closed structure on this monoidal category. And you can see that all of these have this in common. And this is the kind of pattern that category theorists will study. And you can see that abstracting things to these objects and arrows, we can see that really these are all just examples of the same thing. Next slide, please. And so what we're going to do today is we're going to think about a category of not of these types or truth values of vector spaces, but of what I'm going to call interfaces, right? And protocols. So interfaces, I'm going to explain a little more, but you can think of this as some sort of category where somehow we can use the arrows to model interactions between different agents. And we'll think about how we're going to construct that. And this, I'm using this double arrow here because you can think that somehow interactions, we actually want sort of information to flow both ways somehow. So this is going to be some sort of bidirectional relationship. Next slide, please. Yeah, so just a quick formal definition of a category, right? So just to summarize what I kind of informally expressed, next slide, a category is, yeah, so you're going to have these objects. Next slide, please. And right, so for each object, we're going to write that an object, for example, X is an element of a category C. Next slide, please. And between any pair of objects, we're going to have a set of arrows, or you might call them morphisms, or if you want to be fancy about it, you can call them maps between any two pairs of objects. And so you should think of the set as containing all of the possible arrows between these two objects. Next slide, please. And you can express this arrow, as we've already seen, by putting one of the arrows, one of the objects in front, the other objects behind the arrow, and drawing that arrow like that. Next slide, please. Yeah, and we're going to call X the source and Y the target. You might also see this to borrow from set theory called the domain and the codomain. Next slide, please. Now, and the key sort of ingredient for a category is that whenever we have sources and targets matching up between two arrows, an arrow from X to Y and an arrow from Y to Z, whenever we have this, this pair of compatible interactions, we can combine them into a single interaction. So there is always another arrow X to Z that we can denote by G composed with F. And this might feel like the reverse order. This is because of how function application sort of is usually written. Next slide, please. But we can express this just because really we're thinking about this as doing F first and then doing G first. We're going to use this like semicolon notation, which isn't really standard, but I like to try to make it catch on. To express the composite arrow given by combining these two arrows. Next slide, please. And there's some conditions, extra conditions. I won't spell this out in detail, but composition needs to be unital and associative. Yeah, if you know sort of some group theory or some abstract algebra, you might be able to know what those mean. But basically, it just behaves sort of the way you expect them to. Okay, so that's a category. Why do we do this? Why do we bother with all this formalism? Well, I think formalism is helpful. Next slide, please. And oh, sorry, before why do we do this? Let's look at our examples. Oh, yes, next slide, please. Actually, can you go a few more? Just yes, thank you, great. Cool, so we're going to, yeah, so all of these examples we've seen with types and functions, you can compose two functions. With inferences, if X then Y is true, and if Y then Z, you can always combine them to if X then Z, that's a composition. With linear maps, you can compose them if you have a vector in U that is transformed into a vector in V and then transformed into a vector in W, then that's a single linear transformation between those, between U and W. And somehow we want to express interactions that way too. We want this compositional property so that we can talk about these, a category of them. Next slide, please. And again, why do we want this? Next. Yeah, we can, as you can see, we can draw analogies between these things, right? Vector spaces and linear maps is something that's very well studied, whereas sort of these interactions, these sort of protocols between interfaces maybe aren't. And so if we can compare them to something we already know, we can generalize, we can find a lot out just by the machinery of the math that's already out there. Next slide, please. We can abstract away the details and formalize, right? Like everything that's happening here really just depends on these objects and these arrows. And we don't really need to worry about like what's inside of them until we really need to worry about those details. And we can leverage that for our reasoning purposes. Next slide, please. We can maintain continuity of methods. This is a little weird. You might call this purity of methods. I don't really like that term. I like to think of this as, well, so for example, if you're studying if you're studying networks, right, you might want to use graphs to study networks. You might need to use graph theory to study network theory. But then for graphs, sometimes for slightly more advanced techniques, you need to use linear algebra or group theory to study graphs. And then if you're studying linear algebra and group theory, you might need representation theory and so on and so forth. And so you have to kind of like know all of these areas of math, and every time you sort of transfer to a different area of math, there's room for error. There's like room for something might not be modeled correctly, right? Whereas with category theory, next slide, please, there is, so for example, there's a category of categories. And in some sense, if you study the study of category theory, the setting in which you study category theory is just more category theory, and you stay within that. You can think of a category of category. The arrows between them are called functors. Remember that word for later. Next slide, please. You can go further down the rabbit hole. There is a category of functors between two fixed categories, and the arrows between those functors are called natural transformations. Remember that word as well. And this is a little sort of kind of high level for now, but you can see how category theory sort of replicates itself within itself, and you can just keep using those same tools. And we're going to see another example of that a little bit later. Next slide, please. Yeah, and this one's a little more subtle. We can leverage the natural over the artificial. And I don't mean to sort of, I realized when I wrote the word artificial, I wasn't referring to quite the same artificial in AGI, but what I mean by this is sometimes we need to make some very arbitrary choices in math. And the more sort of arbitrary choices we make when we're trying to model something, when we're trying to study something, the harder often it becomes to sort of untangle the math that studies it. And category theory kind of naturally embodies this sort of like notion of naturality, which sort of very informally means that no sort of artificial choices have been made, right? When you saw that currying example, right, you could think of some other different functions that like you could write down from like A to the functions, the type of functions between B and C, but there is this really one very natural choice that you can do. And in fact, category theory has the mechanisms to formally express this notion of naturality. And it makes sort of the computations, things just kind of pop out of the computations, and it just kind of works, which is a little bit mysterious when I say it like that. But I think we'll see some examples of that. Next slide, please. Yeah, okay, so here's where we actually define the category we're gonna be working in. Next slide, please. Yeah, so let's think about what we mean by sort of a category where we have interaction, right? So how are we gonna express an interface? And just by interface, I just mean this family of sets. I'm gonna denote the whole interface by P, and but you should think of this as a index set called I and these other sets called P bracket I. Next slide, please. The index set I, we're going to very abstractly call this a set of positions. So you should think of this as sort of different positions some agents could be in, different kind of different things that they could express. Next slide, please. Yeah, you can think of this as the different ways in which an agent can affect its environment. So for example, if I am an agent, I'm standing in front of you right now, I'm speaking to you, all of those choices I'm making are positions I'm taking. I'm waving my arms around, I'm standing here, I'm standing there. These are all positions that I'm taking that you are then receiving. They're ways I'm affecting the environment. Next slide. Now, at each of these positions, at each element I in this big I, I'm going to have, next slide, a set of directions. And so depending on what position I'm taking, I can receive various sort of inputs or various sort of reactions from the environment. Next slide, please. So you can think of this as, depending on what position I'm taking, the ways the environment can affect me, can affect the agent. And so that's what this structure expresses. Next slide, please. And so the intuition you should have here, which might seem a little weird at first, is that the directions available to me depends on my current position. And so an example of that is if I'm standing like this, right, that is a position I'm taking. You are getting something out of, that's a way I'm affecting the environment. And when I'm standing like this, when I'm turned towards you, you can then the environment around me can then affect me, right? I can see your faces. Some of you are looking at me, some of you are not. No worries. But I can also take a different position. I can stand like this and turn around. And this is something I'm telling you as well. This is something I'm expressing to you as I'm affecting my environment. But now notice that you can't affect me anymore in quite the same way. You could probably still shout and I'd hear that, but if you move, I can't tell. And so really the directions, I'm going to turn back towards you, the directions available to me, the ways the environment can affect me are dependent on the ways what I am choosing currently to affect the environment, to put out in the environment. We're going to use a bit of notation for this, which will make sense a little later. Next slide, please. But you can think of this as, if you've heard of generating functions that model various combinatorial structures, this has a similar flavor to that. If not, don't worry. But we're going to use this notation of this polynomial, right? This sum over the positions, and then we're going to express each direction as an exponent of some formal variable. And so if there are two positions, and for example, and maybe one direction at each position, we might write a y to the power of 1 plus y to the power of 1. And it's this sort of formal sum, and that's why we call it a polynomial. Next slide, please. The benefit of this, and you can start doing sort of like weird things with this notation. It turns out that this I here is going to correspond with what happens when you what happens when you plug in 1 to this polynomial. Next slide, please. Oh, no worries. Yeah. So what happens when you plug in 1 is that 1 goes in here, and now you have a sum over the elements of I of 1 to the power of each of these direction sets. Next slide, please. But 1 to the power of anything is still just 1. Next slide, please. And then if you sum up a bunch of 1s, I times, you get I back. And so that's why we can put P of 1 here. And for any polynomial P of 1 is going to represent its set of positions. And that's kind of a way we're going to use these polynomials. We can sort of like formally think about these in this way. But we're going to we're gonna talk about why we can do this in a little bit. Next slide, please. But yeah, so we can't just, if we want a category, we can't just define the objects. We also have to define the transformations between them. So if we have two interfaces, how can they interact? And the intuition you should have is that, well, how do two interfaces interact? The ways one interface can interact with the other is really just the ways one interface can wrap around the other one, right? You have this hidden interface P, and then you have this exposed interface that's maybe closer to the environment that the environment can access. And so instead of the environment interacting directly with P, the environment interacts with this exposed interface Q. And so what are the ways P can interact? What are the ways P can interact with Q like this? What are the ways Q can wrap around P? Well, next slide. Let's see, and the ways P can interact with Q, we're going to call these protocols. These are also called dependent lenses. If you know what a lens is in functional programming, this is a generalization of that. Next slide, please. Next slide, please. Thank you. No worries. Yeah, so we want, right. So if Q is going to wrap around P, if Q is going to sort of serve as a buffer for P, then for every sort of position that P can express, Q needs to express something to the environment, right? P expresses its position to Q, Q expresses that to the environment. And so this is a function, right? It's not going to necessarily express the exact same kind of position. It's going to model it somehow. Next slide, please. And then once that position is expressed, for each position for P that is expressed, next slide, please. we're going to have another function that tells you how to get from a direction of Q back to a direction of P at that position. So it's going to then go backwards. And I could try to explain this, but let's do an example. Next slide, please. Yeah, so for example, sometimes I know lunch is soon, and so apologies for making you hungry. So yeah, sometimes my partner and I are trying to figure out what we want to eat, and we need to figure it out somehow. So we need to make a decision. So maybe I'm already at the restaurant. I'm at some restaurant, and those are my positions. And at each restaurant, I have a certain set of menu items that I could order from. Those are my directions. Meanwhile, my partner is at home, and they know that there's various cuisines of restaurants that I could be at, and each kind of cuisine usually has a certain set of dishes that they could probably count on being able to order. So for example, next slide, please. There's this really good Thai restaurant in Capitol Hill that I'm not great at pronouncing, I guess, Thai words. But that's the restaurant. Say I'm at that restaurant and I'm communicating to my partner this. I might just say, oh, I'm at a Thai restaurant. So next slide, please. Next, oh, I think we went backwards. No worries. Yeah, and so I'm going to pass that forward, and my instead of letting my partner instead of bothering my partner with directly interfacing with this restaurant, I'm going to just use their interface, and I'm just going to say, oh, it's a Thai place. Yeah, that's where I'm at right now. And my partner, knowing what certain dishes would probably be available at a Thai place, they're going to pick something off their directions there. Next slide, please. Maybe they want some curry, right? And so they pick that, and then now they've made that choice, and they're going to pass that back to me, and then I can serve as a buffer to transfer that to the restaurant, right? Next slide, please. And so given that I'm at this restaurant, their menu is in Thai, right? So I'm going to order kangdang, right? And I know that my partner usually likes red curry when they order, and so I'm going to convert that to the red curry that's listed on their menu, and so that is that interface. That is, so I've used my interface as a buffer between my partner and the restaurant. And that's this, that's our arrow. That's this protocol. Yeah. Next slide, please. But you can compose protocols, right? So to the left here, we still have the protocol between me and what my partner is doing. But right, when my partner is making their decision, they're actually consulting maybe their appetite, right? Their brain, right? And so this is the other interaction that's happening here that's actually hidden from me. So my partner, once they hear that I'm at a Thai restaurant, maybe their brain thinks, aha, that's food, right? I can order some food right now. And so they consult their brain, and their brain tells them that, oh, I think I'm in the mood for something maybe a little soupy, maybe also a little spicy. And so they pass that out to, I guess, their mouth, and they say, oh, I'm at a Thai restaurant. Given that I'm at a Thai restaurant and I want something soupy and spicy, I'm going to order some curry, right? That's going to be an option for them. And then that is what gets passed forward. And so you can see already that you could compose two protocols like this. And in general, next slide, please. If we have two protocols set up, one with each one with a function outward on positions, we can, and functions inward on directions, we can compose them into a larger interaction like so. So next slide, please. Given a position of P, we use the onPositions function to give us a position of Q. Next slide. Given a position of Q, we get a position of R. Next slide. And so this is just an ordinary function composition, but then we have to go backwards. But fortunately, we can take advantage of the onDirections function of this second protocol psi, and at this given position that we already have for whatever direction R gets, next slide, please, that can be passed back to a direction of Q. Next slide, please. And then given this this position of P here, we can use the onDirections function, next slide please, to pass it back that way. And now we've sort of completed this loop. And that's how our protocols are going to compose. Next slide please. Okay, but I sort of teased at the beginning that we can actually set up a closed symmetric monoidal category of these things. And so the intuition here is that whenever we have two interfaces, we can actually think of them as a single interface that sort of like expresses both of their positions at once and both of their directions at once. And this definition is going to reflect that. Next slide. Yeah, we're going to call this the parallel product because we're going to put two interfaces in parallel. Next slide. And it's going to have positions that are ordered pairs of the positions of the two constituent interfaces. Next slide. And its directions are going to be ordered pairs of directions of the two constituent interfaces at those positions in that position pair. Next slide, please. And you could write this in our polynomial notation, right? It's this sort of nested sum. And so since we take, we sum over elements, positions of P and then positions of Q, we're really just summing over ordered pairs of positions of P and Q. And its direction set is going to be this Cartesian product, the ordered pairs between these directions. Next slide. Yeah, and then it turns out that there is also this closed structure on this symmetric monoidal category. Next slide, please. Yeah, so that is, if you remember what we, this pattern that we expressed, the parallel product of P and Q, any protocol out of that is actually equivalent to some other protocol just out of one of these, just out of P, into this sort of like joined thing that expresses the interactions between Q and R. And if you step back and think about what this means, all this is really saying is it's expressing the fact that we can change our perspective for where the boundary between these two interfaces are. So instead of thinking of a conjoined interface with P and Q, from the agent with interface P's perspective, maybe they are just an individual agent, and then they're putting out, they're interacting, the interface that they're interacting with is actually this combined environment between the interface they're in parallel with and the interface that is the target of this interaction. And so this bracket Q comma R is actually an interface that expresses the ways that Q can then interact with R. Next slide, please. Next, I think we went backwards. There we go. Yeah, so the intuition here is we're shifting where that boundary between what's hidden and what's exposed is, from sort of between P and Q and R over to just to fence in P itself. But this is actually completely equivalent. Next slide, please. And in fact, the positions of bracket Q comma R, if you think about it, this kind of makes sense. Are exactly the protocols between Q and R. So when we shift our boundary, right, the positions that P is going to, or the positions of this bracket Q comma R should express all of the different sort of arrangements in which Q can then interact with R. So given when P's position is known, you actually get you figure out how Q's position is going to affect R's position, and also backwards along the directions. Yeah, and so this kind of notion sort of expresses the fact that these interactions, right, like the ways two interfaces can interact can actually be expressed as an interface itself. And this has actually pretty interesting consequences, because it means that in some ways you can express a system that maybe edits its own configuration, right? A system that sort of like changes, that sort of like feeds forward a signal that tells its other parts of itself to change and modify its own interaction, because there's actually this duality between interactions and interfaces. Yeah, next slide, please. Okay, why do we use polynomials for this? This is kind of a formalism. Next slide, please. Why do we call these polynomials? We can actually interpret these polynomials as functors from the category of sets to itself. There's this category where all the objects are sets. And so each polynomial, you can actually think of plugging something into Y up there and then plugging a set into Y up there and getting another set out. Next slide, please. Yeah, just like that. Next slide, please. So a couple of examples, right? You might have, again, if you've worked with functors in Haskell or something equivalent before, these might sound familiar, right? There's an identity functor that sends at each set to itself. You would just write that as Y, and so it has one position, and thinking of Y as Y to the power of 1, it has one direction at that position. There's only one summand, one position, a 1 in the exponent, one direction. Next slide, please. Or you can have constant functors, so sending every set to the same set, for example, 3. And since you would just write this as a 3, it has 3 positions, but no exponents, right? You could think of that as 3 times Y to the power of 0, but something to the power of 0 is just 1, so there's no directions there. Next slide. You might have heard of the maybe functor, which takes a set and just adds adds 1 to it, right? Like it's sort of wrapping around this extra sort of like, oh, this might actually be there, it might not. And this functor, you would write that as Y plus 1, and it has 2 positions with 1 direction. I actually wrote this incorrectly, sorry. It has 2 positions with 1 direction at the first position, but no directions at the second position. Let's move to the next slide because this one's wrong. Thank you. Yeah, so the list functor takes a set and sends it to the set of all the possible sort of tuples of a set. And so you would write this as this infinite sum like this. So it has a position for every natural number n, and at the position n, it has that many directions. And so all of these functors, ways of converting sets to other sets that can be written like this, can then be interpreted as our interfaces. And the really weird thing about this, or the kind of miraculous thing about this, I guess, is that the arrows that the natural notion of arrows between these functions between these functors that I talked about earlier, called natural transformations, actually corresponds exactly to the kind of arrows we want. Next slide, please. Yeah, protocols between interfaces coincides with the usual notion of arrows between polynomial functors, right? If we state this a little more formally, next slide, please. Yeah, the category of interfaces and protocols that I just defined is actually equivalent to the category of polynomial functors and the natural transformations between them, right? And this is a notion that just pops up out of the math, right? Like we didn't sort of like arbitrarily try to like construct it the way like we try to construct the interfaces and the protocols. It's actually already there, which means we can just use the math that's already available there to talk about these things. Next slide, please. Okay, which means we can use the math of functors and we can actually compose these functors, right? Now we're, and this is a bit of a shift in thinking, you have to think about these functors again as these arrows between, from the category of sets to itself, and then we can compose them with each other. Next slide, please. And we get this binary operation between these polynomials. So for example, if we have these 2 polynomials, I'm actually expressing these as these positions as dots and these directions at each position as arrows coming out of each of these dots. So we have y squared plus y and y cubed plus y to the 0 or just 1. And if we think about composing them, all we're doing is plugging in q to wherever we see a y in p over there. Next slide, please. And what we end up with, if you actually expand all this out, you can actually express this. Well, you could do the math, or you can look at these pictures and think, okay, what are the ways to take one of the dot and sort of like arrows from here, and then attach to each arrow some of the dots, one of the dots over there with the arrows. And you get these 1, 2, 3, 4, 5, 6 different positions with the directions, and the directions become a sort of like following a direction from P and then a direction from Q. And this looks suspiciously like some sort of decision tree, right? So it turns out that the composite of two polynomial functors is a perfect way to describe how two interfaces can sort of relate in sequence to each other through a decision tree like this. So next slide, please. Yeah, interfaces in sequence. Great. Next slide, please. Yeah, so for example, we can kind of like spruce up our earlier example a bit. We can actually, right, because a lot of interactions have this like extra step in them, right? I'm not just communicating. I don't just want to know what my partner is going to order. I actually want to know, oh, what protein do they want for the curry? And so I can express this interaction as, oh, I'm at this restaurant. It's a Thai restaurant. They want curry. I hear that. Okay, given that they want curry, I know that the restaurant's going to ask me what protein they want. So I ask them that, and then they say chicken, and then I get back here, right? And so that seems like something that I can't quite express in this language, but it turns out that I can just by thinking of this Q and Q prime as this composite interface, Q composed with Q prime, and that turns out to be exactly what I want. If you're familiar with game theory, this is kind of like expressing a strategy expressing a strategy instead of me passing on the position Thai, hearing back curry, and then passing on another position protein, I'm actually passing on a position Thai, and then for every possible direction that they could sort of give back to me, I have prepped another position ready to go. And that's the position that I'm actually passing. And it can express this sort of composite sequential protocol behavior. Next slide, please. Okay, but what about, I meant to say this example earlier, right? So there's this another way you can think about a, right, so this, and another example of an interaction is maybe an interaction that you have, for example, with your phone or your computer, and sort of boil down really to the basics is that you see something on your phone. Your phone is communicating some position to you. That's going to give you some position, and you're going to pick some direction there, right? Like you're going to pick something, and then basically, right, so your phone is maybe displaying a certain number of buttons. That's the position they're communicating to you. And then the different buttons you can press are the different directions, right? The different buttons you can tap. But this keeps going, right? Once you tap a direction on your phone, a button, it's going to give you something else, right? It's going to express something else to you. And then with more things to tap, and then you're going to tap something else. And then it's going to express more positions, and you're going to tap something else. And somehow your phone has this internal mechanism that churns on, and obviously, right, like it's coded up somehow. But how do we express that in this language? How do we move from protocols like this that sort of just stop there into protocols that keep running? And so if you think about the innards of your phone, you need some way of expressing the states that it could take, right? Like the different states. And depending on what state it's in, it might interact with you differently. And you also need some way of expressing how to get from one state to another, the transitions between the state. And it turns out you can use these composite interfaces to express something like that as well. Next slide, please. Yeah, we need states and transitions. Next slide. Right. And so it turns out that polynomial functors have this natural way of expressing something like this. It's called a polynomial comonad. And so, and I'm going to sort of leave out some of the details in the definition, but the key part of this polynomial comonad is that it's a polynomial functor C that has an arrow into C composed with C, and it satisfies various properties. Basically, so that next slide, please. Yeah, we call this sort of the duplicator, right? Because you're taking a polynomial and sort of like duplicating it into two copies of itself. And what the duplicator is going to do is for each position C, we might call it S sub 0, it's going to pass on that same position to itself. It's for each direction out of S sub 0, it's going to then have another position ready to go, S sub 1. That's sort of the duplication process. And then for each direction out of that, it's going to be able to come back and tell you a direction out of the original S sub 0. And I've given names to this because it turns out that based on the properties of a comonad, you can think of these as the position that this part assigns to each direction. You can think of it as the target. It's giving each direction. These directions used to go to nowhere, but it's actually assigning each direction a position as a target. And then once you have two arrows where the target matches up with the source of the other arrow, you can then string them together into one arrow. And if this is starting to sound familiar, it's because this is just the kind of thing we have for a category. Next slide, please. Yeah, so so one way we can think of this is we're turning our positions and its directions that don't point anywhere into states and transitions, so that like we are actually bending the directions so that they point back to other states. And it's not just a sort of a formal thing. We're actually being able to string together these transitions to produce new transitions that express the composite of these transitions. And so this is just a category. Next slide, please. And this was proven in 2016 by Amin and Ustalu. The polynomial comonads, things like this, which have this duplicator arrow satisfying certain properties, are just categories. And in fact, if you know about any comonad, sort of every comonad that you can express as a polynomial like this in Haskell, for example, is actually going to give you a category. Next slide, please. We're almost done. Yeah, and so we can, oh, next slide. Yeah, actually, just give us the next here too. Yeah, so we can define a notion of a state machine, which is just a something like that phone interaction that we had before. If our source of our interaction, of our protocol, is a category like this, is a polynomial comonad, then it can express a machine's sort of internal states and transitions, how it moves from one state to the next. And then the polynomial P on the sort of outer end is the interface for this machine. And it can, and once you pass a direction back, it'll loop back to some other state, and then it'll just keep cycling through. And a bunch of sort of like different systems. Generally, we would call these like open dynamical systems because they can pass over time, or I guess they have to be kind of discrete. But right, so a bunch of examples of these state machines can be expressed in this formalism, but not just these, also these state machines that kind of like differentiate between how you're transitioning between states. Next slide, please. Yeah, and so, for example, you can see, right, this duplicator lets you go from C to C compose C. And then once you have an interaction C to P, or once you have a protocol C to P, you can kind of copy it into a protocol C compose C to P compose P. And so now you're sort of running through the system twice, and you can keep going. Next slide. Next slide. And you can keep going. Yeah, and until, right, like, and you can just do this in general for any natural number n. Next slide, please. Yeah, so just to conclude, next slide. That was a quick sort of overview of like this theory of polynomial functors. There's so much more you can do with this to express different kinds of interactions. Here's just an example. A lot of these I actually, so there was an implied category theory conference, I think a month ago, and a lot of these were, there was a lot about, and maybe some of them didn't explicitly use polynomial functors, but you can use this formalism to express a lot of these examples. But but yeah, I'd also like to pose the question to you all, which is like, what does this kind of structure remind you of, right? What kind of dynamical system or game or like process, like does this pattern give you insight into, and like, can we use this formalism to express an interesting pattern there? Next slide, please. Yeah, if you want to learn more, there's a book that I wrote with David Spivak, who a lot of this research is like based on. We did an online course. There's videos recorded. There's workshops. There's this great seminar, although I think it actually just ended. But you can find the videos. This is done by the Topos Institute, which is an applied category theory research nonprofit research group. I know we're gonna have a little bit of time for questions, right? But if you have more questions, you can always just find me on Twitter and poke me. I'm happy to talk about this stuff. Next slide, please. Yeah, references. Actually, yeah, that's it. Right, so thank you. Yeah.
Thank you very much for that scintillating talk. We can take one question from the room. I'll take two questions from the room, but if we could keep them short questions as well, short answers, please. Thank you.
Thank you very much for your talk. I'm very pleased to see this material covered here on an AI conference.
Yeah, of course.
My question is, say we recognize this pattern and we want to implement this, try this out. How would we go about that?
Yeah, so there's a lot of different, I think there's a few libraries, right? So Haskell has some libraries where you can implement categories, but since Haskell isn't dependently typed, you can't actually sort of implement the laws that they have to satisfy. But you can still sort of like, if you just like keep in mind the laws yourself, you can model that. Dependently typed languages can actually sort of model the category theory laws. So there's actually an implementation of polynomial functors. I mean, it's very new, right? Like a lot of these things are like just happening, and there's a lot of room to add on to that. But I know a couple of folks, Eric Bond at 26 Technologies, and someone named Amelia Lau, who runs One Lab for it's this library for Agda. They've both worked on sort of like modeling polynomial functors in Agda, and you can so you can implement a lot of these. But there's also a sort of, I'd be kind of remiss not to mention, there's another direction you can go to this where you don't necessarily worry about the laws, and you just kind of like there's this sort of philosophy that, right? Like, for example, I like to say the example of, right, like if you write a program that uses probability, you don't have to like prove the central limit theorem necessarily. Like, so you don't have to necessarily do this. If you want to like make sure everything type checks, like one way to do it is independent type theory. Another way is to just write the code. And so there's some folks at the Topos Institute working on a library called Algebraic Julia, which is expressing all of these category theory concepts in Julia. And there's not so much of the same quite level of like type checking and proof verification, but they're very much oriented towards like actual applications. Can we like model things up scientifically? And they haven't started, I think they were thinking about implementing polynomial functors in that. They haven't quite yet, but there's a lot of like adjacent category theory stuff there. I recommend checking that out. There's some really cool work there as well. Yeah, hopefully that's an answer for that. Yeah.
Yeah, so one direction that has inspired me to think about polynomial functors, which is not yet fully resolved in my mind, is that in working on AGI systems or proto-AGI systems like our OpenCog system, I mean, we're dealing with the concrete level of representation. We have a knowledge graph with all these nodes and links in it, which is modifying based on experience. Yet we know that the real crux of the mind of the system is probably at a higher level, like in the patterns and relationships among the nodes and links in that graph, both at one time and as they're evolving over time. And we don't really have a great formalism for measuring, thinking about, working about, hypothesizing about sort of the emergent dynamical or static patterns coming out of an intelligent or would-be intelligent dynamical system. And it somehow seemed to me that we should have a formalism for this. We're like in physics using differential equations to model patterns over space and time, which doesn't really apply to like an evolving knowledge graph unless you go in some weird limit. So I wonder what you think about polynomial functors as a direction for describing emergent structure and dynamics in like large-scale discrete AI systems.
Yeah, I think it has a lot of potential for that. Like you mentioned, this isn't quite, it's not quite like physics where you have this like continuity, right? You can't quite do it with differential equations. It's just a bunch of graphs. And so actually this language is really well suited for that because it is this like very discrete kind of dynamical system, but that can also model, right, like changes in how things interact with each other, right? And so I think actually, yeah, I would, one of the many references I put up there is a paper from David Spivak and Brendan Shapiro, who are working at the Topos Institute right now on, I don't remember exactly the title of it, but at the Applied Category Theory Conference 2022, if you look up sort of which paper they presented on, it's this one. They talked about how, yeah, you can use actually just exactly the structure that is described as bracket structure to model these like open dynamical systems, like these systems that sort of like learn what's a better organizational structure for themselves and then remodel those organizational structures. And two concrete examples they give in that paper are prediction markets and gradient descent learning. And so they both sort of like satisfy that kind of structure. And so, but they haven't, right, like they're still trying to come up with examples for that, right? Like we're kind of the theorists, right? And so we'd love to see sort of more sort of like practical like implementations of these. But yeah, I would check that out. Yeah, that's definitely, I think there's a lot of potential there. Yeah.
Thanks very much. And we had one more very quick one.
Thanks, super interesting talk. I was just wondering, in a natural language, you can express things that may be logically inconsistent if you evaluate them all together, like the infamous example, you know, the set of all things that are not parts of sets or elements of sets, for example. So there's parts of that that are semantics that are expressed. It's not just a bunch of words. There's things that can be inferred from that. So can you do that type of representations with your approach without, or does the formalism break it?
Let's see. That's an interesting question. So yeah, so there's a certain ingrained, I'll kind of take this in two directions. Apologies if I don't exactly interpret your question, but there's a certain determinism in this, right? That, yeah, you kind of have to like define sort of exactly what kind of relationship you're having with between these other interfaces, but you can still then model those interactions with another dynamical system, right? So, or another one of these state machines. And so you can, right, like if one of those, if you think about, right, like that sort of like C on one side, P on the other side, right? Like if you don't know one of these things, right, like you are, yeah, you can think of a problem where you model something where you don't actually quite know exactly what this structure is. No, that's a very interesting question, right? There are applications in just like wider applied category theory of how do you interpret like natural language semantics within category theory. And category theory gives you a great way to do that, partly because it's not, you don't have to express things linearly, right? Like we had this example of like, you can compose things, right? You can put these arrows together, but you can also have this other operation that puts things next to each other. And in fact, you can have multiple operations that put things next to each other. One here, I say you can put them in parallel or you can put them in sequence. And then so you have all of these different operations to put things next to each other. It's not just one-dimensional line of like of words, right? And so you can express these relationships in category theoretic terms. Bob Koch does a lot of this at Oxford. I think he was originally studying like quantum computing stuff, and you can model a lot of that in category theory, but it turns out the same formalism used for that, again, it's one of those pattern things. This shows up also in natural language modeling. And so I check out, I would look into some of that. And I haven't really thought about how to relate this back to like specifically polynomial functors, but there might be something there. I don't know. Yeah, it's a very interesting question. Yeah.
Thank you very much indeed. Fabulous way to end the morning's talks. Big clap. Thank you.
Thanks.